Let's do the quick software overview so we can get into our first example. When we say NDN software, what might that mean? And a way that I think of this is that there are different collections of NDN software. Certainly, if you take this broadly, including a lot of different work going on in different places, and I'm sure, in fact, that this is not an exhaustive list. But I thought I would show you this list to begin with. Now, the two things that are in red, that are highlighted in red, these are the software collections that we're mostly going to deal with, be involved with in this workshop. You will hear about another one of them in a talk that Alicia is going to give tomorrow. And on Wednesday, we'll probably talk about at least one other as an example. But the hands-on component is really focused on the ones in red. And that is the CCNx open source, which I'll say more about in a moment, and the Python language bindings that are available for it. So we're going to actually start with Python in our first NDN example because it supports very clean, simple programs for simple things. And so we're going to start with that. If any of you are interested in Python, the thing you need to know is that the Python language bindings are not part of the CCNx distribution. At least not yet. They probably will become part of it at some point. But they aren't yet. So if you have CCNx installed and running, that's great. But if you want to play with the Python stuff, you need to get it from GitHub. So you need to do another clone from GitHub. And that URL is also, I believe, on the website of the workshop. So you can grab it from there and not have to retype it. But if you want to play with Python, that's what you need to do. So these, particularly CCNx, are kind of the core software collection that many people are able to build on and do a variety of interesting things. We've listed here some of the specialized tools that people are working on. These are examples all from the NDN project in the United States, although others also have been working on an S3 simulator. If you have questions about some of these kinds of things, you'd like to get your hands on them. Some of them may not actually be quite ready to have outside users yet, but if you're interested in any of them, please talk to us sometime in this 3 days so we can hook you up with the right people and get you access to those things. And if these are more tools, then this group at the bottom is more applications. These are applications in the case of something like the audio conference tool that we're actually using on the NDN testbed we have in the United States. And we're using it on a weekly basis to actually have conference calls among different parts of our teams. The multi-user chat is something that you're going to hear about from Alicia tomorrow. So you'll get a little more of a dive into that application then. NDN lighting is using NDN in the context of instrumented environments and controlling lights and building and things like that. And we'll probably talk about that a little bit on Wednesday. And the list goes on. This is not an exhaustive list. So one of the things that I wanted to do in introducing this is to point out that there are a whole variety of collections of software. They're maintained and built by different groups of people. They're not all exactly the same group of people. And we would love to have more additions to this list and things that we can point other people to that could come from all of you. So please, again, think about getting involved in various ways. So even though we're going to focus largely in this workshop on some core things in CCNx and using the Python language bindings, I don't want you to get the idea that that is all there is to NDN software. Since that is what we're going to focus on, though, I'll say a few more introductory things about CCNx. And that starts with the core protocol. This is the interest data protocol. There's implementation of that, sort of wire format stuff. And here are major things that we find in CCNx distribution. We find this thing called CCND, the CCN daemon, and it is basically the forwarder for NDN and CCN packets. Relatively new thing is the repository called CCNR, and that is a component that provides access to named packets of data that are stored for a long period of time. So we'll touch on that. Within the CCNx distribution, we have C and Java libraries. So when you write applications, what's currently supported is to use C, to use Java, or with the Python bindings to use Python. Now, the way the Python bindings work is that they are built on top of the C library, and they stick fairly close to the C library, but with interfaces that are more adapted for Python style, etc. And so the Python bindings actually sort of stick close to the C library. The Java library is different, and one of the things to be aware of, if you haven't discovered this already, is that the different libraries have different functionality. And that's not because somebody decided that we need something in Java that nobody will ever want in C. It's a consequence of the historical development. There hasn't been enough time, understanding resources, etc., to go and make all of these completely consistent. The two libraries, the C and Java libraries, and this is also true now with Python, both have a style that is sort of adapted to the language environment. So they look very different in style. The code that you're writing looks different. But in theory, the same sorts of functionality should be available in both. And a lot of the core functionality is available in both, but you'll find differences and variations where there's more support for certain kind of things in C and more support for other kind of things in Java. So again, don't take any of that as fundamental. We do have support for Android now. And there are various utilities running around, some of which we'll touch on in this workshop. One very significant one, of course, since we're dealing with networking, is a plugin for Wireshark. So what that means, it's actually a Wireshark dissector, which means that if you capture packets, CCNx packets, encapsulated in IP that is running either on UDP or TCP, because that's what the current CCNx libraries and CCND do. They do encapsulations in UDP and TCP. So you can do packet captures, packet traces with Wireshark or TCP dump or something. You can take those packets, load them up in Wireshark, and we have a plugin that provides the dissector that will actually decode those low-level CCNx packets. So we're going to do some looking at packets in Wireshark during this workshop. One of the things that's unfortunately more difficult than you would like is to actually get Wireshark built so that you can build the plugin. So if you've had some struggle with that, we completely sympathize. And you can come talk to us about that as well. And then the CCNx distribution also has some sample applications of various kinds. Depending on how long you've tried to be doing something with CCNx code base, you might have run into one called CCN Chat. But a lot of people use a little text chat program, and we're going to see those, some of those kind of ideas coming back in the homework and things. One of the things to caution you about the sample applications comes back to the point about this not being finished. The sample applications are far from perfect. In fact, in the boot camp that we did in September, we used the CCN Chat application as a major example. And by the time we finished the discussion of that example on that first day, I think most of the people in the room had concluded that CCN Chat is actually an anti-example. That is, it's more an example of what not to do than it is an example of what to do. So please, take every advantage you can of the sample applications, but don't expect that just because it's there as a sample application, it is some perfect, shining example that has been carefully polished to be either an ideal case of how you should do something, or even more importantly, something that is designed to be really easy to understand. Unfortunately, we don't have a whole lot in the way of examples that are designed to be really easy to understand, to just help teach you something. And similarly, and I didn't put on this list, but the CCNx software distribution also has a whole set of unit tests, and those are very important in helping us to avoid at least some regressions as things change. You run the test suite, make sure you have broken things. But the test suite especially is not a good example of how to do things, because there's a variety of things, especially in the Java test suite, that are done in order to enable testing that could be very confusing if you go and look at that purely as a sample program of how to write something. So be a little cautious about that as well. It's always a good idea to start out with a bit of a picture of what's actually in a release. I recommend the README file to you for this because it gives a bit of an overview, but just to get started, I wanted to touch on a couple of things here as well. So there is a configure script. It's more of a hand-coded one than the kinds you may find in a lot of other open source projects. So you start out to build by configure and make and that sort of thing. When we started this out, we decided to separate the Java and C components fairly clearly in the release tree. So C source is where you find all of the source for the C parts of the system. And that includes the forwarder. The CCND is a C program. The repository, CCNR, a number of the basic tools and utility commands. After you build, the bin directory should be populated with all of the common commands that when you do make install, then they install in the appropriate place, like user local bin thing, so that you have access to them even wherever you are on the machine. But a bunch of those things are C code, and so they all live in C source. Java source is where all of the Java code lives using the directory hierarchy for package names the way Java works. And there are also some utility programs. Some of the things that end up in bin, some of the commands that you can run, like CCN put file and CCN get file, if you look at those, they are not actually executable programs directly. They're scripts, and those scripts run certain Java classes. So even within the commands in bin, you'll find a mixture of things whose implementation is in C and whose implementation is in Java. I want to point that out. Include is, of course, for the C header files. Doc is where you'll find in the distribution tree a lot of the documentation. That includes man page source, as well as the documents that appear in for easy access on the website. And here's a picture of the documentation page, a recent version of the documentation page on the website. And I want to switch to show an example of this live. So the way that this has been broken up and organized is that we've got the information about the protocols specifically separated in its own category. So the protocol description is a kind of overall high-level thing. If we go to the protocol specifications, you'll see that there's all of these different pages that, for example, give you the overall CCNx protocol. The interest message is something we're going to be looking at in this workshop, is what does an interest look like? The content object is the name for the data packet. So this is where the format and contents of the data packet are specified. If you haven't encountered it before, the wire format that CCNx uses for all of its packets is not the conventional wire format of fixed length fields and a fixed header. Instead, we use an XML style of data model. So it's very flexible and can be extended in various ways. But the wire format is not XML, which is a text encoding. Rather, we have this binary encoding that gives a very efficient encoding representation of the packet content and packet headers, but it still preserves the sort of information model of XML with a notion of nested tags. And so the specification of that efficient binary encoding is the CCNb page. So if you go to any one of these, and I'll just pick that one as an example, actually this one is a little bit skeletal. Go back and look at interest message. You'll find things that tell you, okay, what are the fields that an interest can have, many of which are optional, indicated by those question marks. And again, the binary wire format encoding allows us to easily have optional fields and support optional fields. And when those optional fields aren't required, they're simply omitted from the packet. So this is the protocol technical documentation. Now, in addition, we have software documentation, including Java API docs. You can see all of our classes, and root around in them, and C API documentation, where you can look at data structures throughout the code. This is all documentation that's generated out of the source code, out of Java doc and similar annotations in the source code. There's also some specific documentation about CCNx for Android. I don't know why that link is not working for me, so we'll have to fix that. All of these things, so all of these things that we looked at so far in protocols and software documentation section, they actually they all come from this software release and distribution. So you'll find things like protocol specs under that doc tree, and you'll find the API documentation, of course, woven through the code. But for convenience, it's always available here on the website. You can, of course, build all of this locally and have local copies of the pages if you want. So that was the documentation, and just seeing if I missed anything significant. Experiments is some code from some particular historical experiments we ran that we wanted to make generally available. Schema. Schema is probably worth mentioning. As I said, we use, for the packet formats, we use an XML data model. And although the wire format is the sufficient binary encoding that we call CCNb, there is a translation possible to text XML that you can actually read as a human, much more easily than you can read the binary encoding. And accordingly, and to keep track of all of this and specify in a central place what the packet formats really are, we have a schema directory that has XML schema for these different packet formats that are defined. So you can look in there to find what should be the sort of official truth about what the packet format is in any particular release at any particular point in time. It's not necessarily the case, say with Java, that the implementation actually depends on the schemas. So I warn you that it is possible for the formal schema specification to get out of synchronization with the code that's supposed to implement it. So, of course, we try to prevent that from happening, but that's a warning that that can happen. But this is where the official schema is supposed to be stated. Now, as we start to turn to running some of our first examples, I wanted to show you this picture to talk a little bit about when we're running CCNx code, what are we running? And what does the arrangement of processes look like on a typical node running CCNx? So the core and the heart of this is the CCND. The CCND is the packet forwarder. So basically the idea is that nothing moves except if it goes through a CCND. The CCND in the current implementation is this portable C program which runs in its own unique user-level process. So the typical configuration of your node is there's one CCND running. And that CCND is serving as the forwarder, and that means that it's doing something that's directly analogous, same idea, as what the IP stack in the kernel of your operating system is doing when you're using IP. Now, ultimately, the functionality of the CCND forwarder should be in the kernel of your operating system, but that's not a step we've got to yet. So the CCND is still running as this user-level process. One of the reasons you want to have it end up in the kernel is simply for efficiency. Because every one of the programs that's using CCNx that are all represented by these dashed line surrounded boxes, these are all communicating with each other and with other nodes, with other machines on the network through their CCND. And so it would be more efficient if some of that was in the kernel, but we're not there yet. Now, an application that's using CCNx has the code of its application, and that's going to be bound against one of our libraries. So you can think of any of the three, C, Java, Python. And the dashed lines are here to represent process boundaries. So when you're running an application, you've got a process, and inside that process is your app code and the library. And these thick black lines that are here within this box, the box represents one machine, like your laptop. The thick black line represents a connection that the library makes to transfer bits between itself and the CCND. Now, the two libraries do this a little differently. The C library uses Unix domain sockets for this connection, and the Java library actually uses IP because it's hard to use Unix domain sockets from Java. And so it makes local IP connections and runs over UDP, or by default, actually, TCP between the library and the CCND. Now, one of the things that's very different, and this comes back to our thinking differently, is that the boundary of functionality that you think about in today's programs between what sits in libraries, say, bound to your application in the application process, and what sits in the kernel today in IP, and then you think about the analogous boundary between what's in the app for CCNx and what's in CCND, it's rather different. The CCND does very basic forwarding operations, but the applications are actually speaking the CCNx interest data protocol even across this line. It's not like you open something like a socket and pour data into the kernel, and that data gets packetized and handled and sent out on the wire by the IP implementation in the kernel. That's what we're used to from IP. That's not what happens in CCNx. In CCNx, once a data packet, for example, leaves the process of the application that produced it, it is already a piece of named data. It is already in wire format. It is signed, and that means that it's immutable. It carries its name, it carries its data, it carries its signature and identification of who produced it that made that signature. And all of those things have happened before it ever gets to a CCND. So and there are good reasons for this, and one of the important reasons for this is it has to do with building these security trust foundations into the communication of data between producers and consumers. So it is the application that knows all of the context that's needed in order to determine how should I name my data, which goes to how it's going to be packetized, because every packet has a name. It's the application that has the context to know what keys should I sign this data with, so that my intended consumers will actually trust the data, what Van was alluding to earlier. As a producer, you have to produce data that your intended consumers are going to be willing to receive and that they're going to be able to trust. And that's something that the application knows, and the application has context for. And similarly, if you're dealing with private data and you need to deal with encryption and things like that, that all also belongs to the application. So by the time that packet has left the address space of the application that produced it, it is ready to go anywhere in the world as a wire format CCNx data packet. And it could be used by a consumer that's another app running on the same machine, or it could be used by a consumer who's another app running on the other side of the world. And it won't matter, it'll be exactly the same data packet. Similarly, when apps want to obtain data, they use the interest packet. And again, through the library, so that people don't have to rewrite all of this every time for every application, the library provides the common parts, but when you ask for data, you send an interest, and that interest packet, when it leaves the library and the address space of the consuming application, it is a wire format CCNx interest packet. So what the CCND does is it does the forwarding of all these things. And we have these little colored symbols in the corners, and they represent a concept in the CCND called a face. And we use the term face as a generalization of the idea of interface that you're familiar with from IP. And the reason we call it face is because these are not just hardware interfaces like an Ethernet card. As we see in this picture, here's a face that is directly connected to a local application. The yellow face, or let's take the green face. The green face, what this is supposed to represent in this diagram is that we've got a off-the-machine wire connection going on there. So this one illustrates something like running over TCP unicast. So a point-to-point connection to some other machine running a CCND. And that's a scenario that we're going to recommend to you for the homework exercise. We're going to have a hub machine so that wherever you happen to be working on this, whatever network you happen to be in, we can sort of pretend that everybody's in the same broadcast domain. So that's an example of a face that involves real communication over a network off the machine, as does this one represented in yellow. Now the difference between these two in this diagram is that the yellow face is a broadcast or a multicast address face. So there might be a whole bunch of recipients out there, and the CCND doesn't even know who they are. And as Van was saying in the introduction, NDN is very broadcast friendly. This is perfectly fine. You don't have to have an address of a party to the other side in order to communicate with NDN. So consider the orange symbols to represent local faces, and this is one of the distinctions of a face. There are a bunch of flags that a face can have, and one of the important factors is it local? And local faces are treated a little differently in certain circumstances from non-local faces. Here's a remote unicast face. Here's a remote broadcast or multicast face. Now, we've also shown on here the repository program, CCNR, and a program called CCNDC. CCNDC is a control program for CCND. It's the program that you use in order to change the FIB, the forwarding information base, that is a part of the CCND. And you'll see, although they're colored differently, to reflect the fact that they are more like core utilities or tools of CCNx. You will notice that otherwise they look exactly like these green colored things that are supposed to represent applications for the end users of the communication service. And that's because their implementation structure is really exactly the same. Each of these runs in its own process. The CCNR as a repository would typically be a long-running process, like the CCND itself. The CCNDC, in many cases, is used like a route add command. So its process may only run for a short period of time in order to do something to CCND, but each of them runs in its own process. It uses some of the same library support that applications use. So even though they're utilities and they're sort of a part of the core system, they are nonetheless very much like applications. They have the same relation largely to CCND. So when we turn to look at a first example, we're going to be looking at an example program as an application. We're actually going to look at a producer-consumer pair. And so these will be an app with a library, and that library will take care for you of establishing a connection to the local CCND on your own machine. And as we begin looking at examples, we're going to start by ignoring the case of external nodes over here. We're going to start looking just at applications running on the same machine, simplest possible case, and communicating a producer to a consumer running on the same machine through a CCND that is local to the same machine. The CCND is also, in addition to having the FIB, which controls the forwarding of interests, it's also where the so-called content store lives. And think about the content store as playing the role of the buffer memory in a router of today. That's the idea. But as we talked about in the Thinking Differently section, this is a memory, so everything that goes into the buffer memory in here has a name, and it can be reused if somebody else wants it within a short period of time. And finally, the third piece that is also in the CCND, that if you've read the Conex paper, for example, you'll have read about these three abstract data structures, the FIB, the content store, and the PIT, the pending interest table. And the PIT is also implemented in the CCND. It's all part of the forwarding plane of NDN. So when an interest is sent from an application and it can't be immediately satisfied out of the content store, then that interest may be forwarded on somewhere else. And in our first examples, the somewhere else is going to be another process on the same machine, because that's all we're going to have at the very beginning. And the record of where it came from is maintained in the PIT, so that the data can follow the path in reverse, going back to the consumer. Okay, that's a whole lot of stuff. What I want to do now is take some questions, and then I think we should take a short break. And when we come back, we're going to start looking at a very simple producer-consumer kind of example from IP, actually, not from NDN, and then look at the NDN analog and get started on examples that way. So are there any questions anyone is brave enough to ask about anything so far? Okay, then I think we should take probably about 10 minutes. Does that seem reasonable? So that clock, which I'm pretty sure is a few minutes fast, but we can go by that clock because it says exactly 10:25. So let's come back about 10:35.